because I've got my dependent variable v, my dependent variable y, and independent variable t, right? That doesn't work out. So the trick here is to rewrite dv dt as dy dt times dv dy, which only makes sense because we're in one-dimensional motion, which then gives me v dv dy plus y equal to 0, which then you can solve, as I do in example 5.9, and like we did Wednesday. Yeah. Well, you can separate, you can integrate. Once you do that, then you have to integrate to solve back for y. Like this, you separate, then integrate. This gives v equals to stuff, all right? And then, well, v is dy dt. And then you integrate the stuff, and that gives you y.
But that'll give us dy dt in terms of y. And we can't really integrate y in terms of t with the function t, right?
Oh, that's fair. Oh, I got you. Wait, what?
You did y prime equals v.
Wait a second.
Oh, yeah. That's right.
You're working on a different problem right now. What we did in class.
No, it's fine. It's fine. So this is stuff in y. Excuse me, yeah, stuff in y. All right, v equals stuff in y. Right? You've got dy dt equals stuff in y, so you can separate and integrate. Yeah, it's fine. Whew. I'm very gullible. You can bring me into it. Like I will get sucked into the confusion if I'm not careful. But yes, this is a formula in y, and then we can integrate it. I mean, I can tell you specifically what the formula was. It's on page. Try not to reinvent the wheel here at the moment, you know. Let's see here. Where'd this thing gone to? Specifically, the formula was v is plus or minus the square root of, you know, c minus y squared in the notes. I think I had a c squared in class, you know. And then we found an inverse sign as the integral, so forth and so on. Yep.
Can you please just explain that step again where you change dv dt to dy, dt dv dy? It's still.
I mean, I can tell you what I said before, which is this is the chain rule.
Okay.
It's the, you know, chain rule in reverse, I guess, is a more accurate way to say it. We're imagining writing the velocity as a function of position rather than time.
Okay.
And if we do that, right, if I say v tilde is equal to v of t written as a function of y, time as function of y, then I differentiate this with respect to y. Well, then that is, by the chain rule, dv dt at t of y times dt as a function of y, which then solves for dv dt of t of y equals to 1 over dt dy dv tilde dy, which then gives you dy dt, because that's how the, if we can write one as a function of the other function of the one, the derivatives of the function and its inverse relation are reciprocal. But we don't want to say all that. We just shortcut this by saying it's like this, right? But this is a shorthand for this blah. There you go. Did that help? It did not help, right? So I shouldn't say that.
Yes, sir. It
No.
makes a little more sense.
But I'd rather say we just think of, you know, inserting a y is in some sense like multiplying by 1 here.
Yes, sir.
But it is, fair enough, it is, underlying idea is you're writing v as a function of position, which means that you're taking the time and you're rewriting the time as a function of position, and then you're differentiating that. It's a chain rule. But other questions? Okay, I wanted to. So I have some neater examples. So I did also bring my book. Are there any questions about the recommended homework? If not, it's fine. But I'm going to stop bringing this book to class because it's really heavy. We used to make all the students carry their book to class every day. Can you imagine that? Phew. Goodness. Let's see here. While we're waiting for my computer to behave, oh man, where'd it gone to? Oh, there it is. So I have some, I think, nice examples in the notes that I'd like to talk to you guys about. Huh. Oh, that's weird. I had to press the stop presenting media button to make that go down. I hope this works. I feel like we may be in some sort of intermediate state where, all right, well, all right. While we're waiting for this to warm up, you asked me about like how to create a differential equation. I forget who asked me. One of you asked me how to create a differential equation that has certain features, right? So like if I want a differential equation which has horizontal tangents, you know, where sine is 0, where sine of x is 0, what I would do is I would just write, you know, dy dx is equal to sine of x. If I did that, then wherever sine of x is 0, I'll have a horizontal tangent. Right? If I want a differential equation which has a vertical tangent wherever cosine is 0, I divide by cosine. See, then whenever cosine is 0, you have your derivative blowing up. That's basically it. Those are the two tricks. If you want horizontal tangents, put it in the numerator. If you want vertical tangents, put it in the denominator. Those are the games we can play. All right, so I actually have some kind of, I think, interesting calculations in here to share with you guys. So I did some of them yesterday, right? We did like the, you know, you guys remember, we did the population, we did the charging capacitor. Here, this is find a family of curves which is increasing. Find a family of curves which is increasing between, you know, whenever you're before or after plus or minus 2, and in between minus 2 and 2 it's decreasing. And so I argue here, well, if you want the quadratic y plus 2 times y minus 2 is like that because it's positive before and after minus 2, if you just think about the graph of a quadratic in y. And so if I set dy dx equal to that, that's the differential equation that I would hope would have this feature. And if I separate and integrate partial fractions, and then there's the answer, all right? And then you can look at it. And in fact, it works. Like here's the picture of the differential equation. It's increasing, you know, above 2. It's decreasing between 2 and minus 2. And that's what it looks like. So we can play these games. This is the discussion about orthogonal trajectories, which we've already had. Here is the friction force. Here's a friction force example with the calculus actually done out. So I hope I set up the framework today. Zoom out a bit here. So whew, my eyes are fuzzy. Let's see if I can get my pointer out. So if we have the friction force equal to minus the velocity squared, then we can find velocity as a function of time by doing separation of variables, right? So separate like that, integrate, and then put my initial condition in. This is a trick. If you want to put initial conditions in, you don't have to solve for the dependent variable. You can just plug it into the equation where you are. This is sometimes labor saving. So I plug time 0 and v naught in here, and that tells me, in fact, that c1 is the negative reciprocal of my initial velocity. And then I do the algebra, and here you go. Velocity as a function of time is this. So what's the velocity as time goes to infinity? Think about it. As time goes to infinity, the denominator gets super big, right? Or super small and negative if v naught's negative, I guess. Anyway, this goes to 0, right? Velocity goes to 0. All right. And, well, we can also integrate to find the velocity as a function of position. And if we do that, I end up with this. So if we calculate the position as a function of initial velocity, I get this. And so that's interesting. Why is it? It's slightly counterintuitive, I say, because the position is unbounded, even though the velocity tends to 0. Notice this is the position as function of time, rather. As time goes to infinity, what happens here? You've got log of a super big number, which blows up, right? So how can this seems counterintuitive, doesn't it? As time goes to infinity, your position is unbounded. And yet, as time goes to infinity, your velocity goes to 0. So just because your velocity doesn't go to 0 doesn't mean that you don't keep going and going, right? Yeah.
Do you have to use L'Hopital's rule because you also have... Oh, no, you don't.
It's possible, but not this one. Not this one, though. Newton's law of cooling is, a famous differential equation, which is interesting. Again, we can solve it with the methods that we have. So Newton's law of cooling simply says that the time rate change of the temperature is proportional to the difference in the temperature of the object and the ambient temperature. All right. So in other words, if you had a cup of hot coffee, how fast it cools is based on the difference between the temperature of the coffee and the temperature of the room, right? You put the coffee in a room of the same temperature as the coffee, it's not going to cool, all right? But otherwise, you can, in fact, this is an example of one where you could either do separation of variables or integrating factor. Because if you look at this, that's a constant, right? So you could solve this for like dt over t minus r is an integral you can do. And minus k dt you could do, right? So this one you could either use separation of variables or integrating factor method, truth be told. But if you do the integrating factor method, run through it, you get this as your solution. The temperature as function time is the room temperature plus a constant times e to the minus kt. What happens as t goes to infinity? The temperature goes to room temperature, of course, right? So that's fun. These problems are challenging in practice because they require two constants. There's two constants going on. There's the one that describes the coupling of the energy to the ambient, to the room, and there's also the room temperature. So these are, while they're first order differential equations, they require two parameters to set up. I also have this voltage across a resistor, but you can look at that. The one I wanted to talk about in the last second here, oh man, I guess, well, there's the mixing tank problem. This here is population growth where you also have a death rate. If you have a death rate proportional to the square of the population, you end up with a differential equation that looks like this. And if you factor p out, you get this differential equation. The significance of c is it's the carrying capacity. All right, so like once your population approaches this carrying capacity, population growth goes to 0. For example, if your population was equal to c, it just stays at constant c. That's this model. And that's essentially the same math as the one I talked about just a second ago here with the y plus or minus 2. Again, it's partial fractions. You work through it, and you get this formula. This one amuses me greatly because I have a differential equations book which mentions this 1920 paper that found this kind of formula with these constants to model the population in the US. The carrying capacity is 210 million and like this. And it matches the population in like 1850 and 1950. But what's the population now? 300 something, right? So it's just wrong. Anyway, it doesn't work. Then at the end of this, I actually work out some variable mass problems. Here, I solve the differential equation that models a raindrop, which is falling through a cloud and so forth. Let's see, this one is what? I have two. This one, a water vapor adheres to the raindrop. Anyway, I find the velocity as a function of time. And this one actually has a terminal velocity. As time goes to infinity, that goes to 0, and you get minus g over k. But anyway, if you're interested, you can read them. If you're not, it's OK. Just do your homework. Do your homework. Homework's due when?
Monday.
Monday. OK. Sunday? No. I'm not going to be here. Let me hit can you hit the stop record on that for me? Thank you. Muchas gracias.